In the meanwhile, today, we're going to work on something different. We're going to talk a little bit about tool sets that will help you in your assignment. Okay. And then in the second part of the class, you guys will get together as teams, and you will have a whole hour to discuss whatever you want. Yes?
Are you going to post the grades for the other two homeworks?
No, I'm going to give it to you right now. Oh, to the assignments? Yes. The Moment Fish, now that he's back from China, and it's good that he's back from China, he's going to post the assignment very soon, according to him. He is the one who has all the script to evaluate everything. So I know that it's way late, but, you know, academics, we're always the last moment possible and, you know, always procrastinating.
Killing me.
All the time. Okay. So this is a brief tutorial followed by an online sort of exploitation example. Can we close the laptop, please? Thank you. And without any further ado, let's start talking about the first tool. That all these tools are suggested; they're not mandatory. You will not quiz on it or anything like that. I find them useful for a number of reasons that we will see in the rest. The first one is Radair 2. You know, read the documentation. It's Radair is actually a tool set of different tools. The most used one, if you want, is the disassembler, but the main tool uses the other tools for various parts of the analysis. The cool thing, at least for me, is like TCP dump and other command line tools is a tool that you can script, that you can use to extract information about binary on a large scale because you can script it. And so it is very useful. It's complex and powerful, also has a very steep learning curve. So imagine, you know, learning VI usually is a nightmare. It's, you know, all these DR one-letter commands allow you to do that. But once you are familiar with those commands, that is awesome because with a few keystrokes, you can do amazing stuff. I'm not a VI fan, but, you know, I definitely realize how powerful that approach is. Also supports ASCII-based visualization, so you can have nice graphs in ASCII. Can be scripted and supports debugging. And is based on a number of other tools like Keystone, Capstone, and Unicorn that allow you fundamentally to emulate binaries or binary code, and therefore, you know, can disassemble well, can emulate well, and all that cool stuff. Just to give you an idea of what the tool set is, we have Radair is actually disassembler, but then we have things like Rabin 2 that extracts information, command line assemblers, hashing, binary diffing tool, you know, pattern matching for binaries, and, you know, you can even have program launchers and other things that are very interesting. I sincerely find it very useful. We will use it today to look at this very simple vserver, which is a vulnerable Linux servers that has the echo command. So you send a string, you get a string back. And we will see, especially for the one here that are not experienced in binary analysis, how you can go around and trying to find out what a program does and how to come to the point where you're actually starting to exploit it. And this is, of course, you know, how you have to compile our server. You know, this is because you want to have all the possible vulnerabilities easily exploitable. For example, if we compile our vserver and we run Rabin on the server, you can see this will tell you the various sections. Remember, you know, in ELF file they have sections and segments. This is, you know, something that could be useful to understand, for example, what are the permissions of the various segments, or you can extract just the header if you're interested in knowing, you know, what is the entry point or where you are in the file. Another example is that you can extract information in JSON. So instead of just printing it, returns a JSON structure. So you can script this, load it, for example, using a JSON parser like in Python into data structures, and then you can use it, for example, to do machine learning. If you want to learn, if, for example, certain headers are indicative of a file being malicious or not, you can use this as a way to extract information in an automated fashion. But the actual sort of main use is RADAIR2 or R2, which is the main shell. Two things to know. There is a pretty complete help system even when you use it. So whenever you're confused, you usually do a question mark or an H, and you get some information about what's going on. And you can also save projects. So for example, if you're analyzing a binary and you find certain function, you give certain names to function or to variable. You can say, oh, this is probably a counter. You add a comment. You want to save that. So when you reopen the same file, you actually have that information available. And the cool thing is that you can, when you launch commands in the shell, you can combine it with grep and more to actually see what's going on. One thing to know about RADAIR, once you open, you are at a certain location. So you are at the program remembers, like a debugger, where you are right now in the analysis of the program. And the command S, seek, allows you to move wherever you want. So if you do S, 0x, 08, 04, something, an address, suddenly that becomes your new address in the file. P prints stuff. There are many variations. RADAIR works by having a basic command and then other description. For example, PDF will be print the disassembly of a function. So this makes sometimes the commands difficult to remember because there's so many options. But you can put PH or P question mark, and you will see the documentation of the possibility that you have. Cool thing that we will use is write. So different from other editors, RADAIR makes really easy to binary modify a file. So if you want to change the binary for some reason, you want, for example, a version that skips a check so that you can execute it and you don't have to put the password because it's password protected. This is a great way to use this. Of course, in order to do this, you have to open the file with a W option, or there is a serious command called OO that changed the way in which RADAIR is operating. So you do OOH to find out all the different possibilities. You also have a set of properties configuration. This is just a very simple tutorial, but with E, you can set, for example, the type of syntax. I want to see assembly in Intel form and not in the other form. And also, you can have expression. You can specify very complicated things. We'll say, oh, I want this command that disassemble starting in this particular address for this much, et cetera, et cetera. So you can go very sophisticated. Sometimes it's useful to have always a cheat sheet that tells you how to do it. Also interesting analysis. You almost always you run it with a -A option at startup to say analyze anything that you can about this binary. So it finds or tries to find the functions, the jump, where the global variables are. Otherwise, RADAIR fundamentally opens the binary and waits and puts you at the starting point and saying, okay, now what? But instead, if you start the analysis, at least you have some of the symbols if they're available. You can also use RADAIR as a debugger. So you have a bunch of commands that you can imagine to, for example, set breakpoint, continue execution, read and write, continue until fork. You can have a lot of other operation. I personally don't use RADAIR for debugging as much. I prefer GDB, as we will see with PwnDBG as an extension, but that's my personal preference, okay? In these things, it's up to you. Thank you very much, Fish. There are functions. We saw analyze function. You can see that AFL, list function, analyze function information. You can ask information about a specific function, where it is, how big it is, and so forth. You can rename it. And of course, you can find cross-references. So you can find all the places that call this function and all the function called by this particular function, which of course create a control flow graph. Other set of instruction, you can see I provide information, and these modifiers tell you, for example, show me all the strings in the whole binary, show me the sections, the symbols, link library. So this gives an idea of how Radar works by giving classes of command, first letter, and then the second letter you just specify different subclass of command, and at the third letter a subclass of that command, and so on, which can create sometimes cryptic thing, but that's why you have to have a cheat sheet available as much as you can. Flags are also labels to put information on various items, so you can flag things and remember their functions, and they have namespace. Interesting, there's also a visual mode that you switch with V, and you can sort of switch between different visual modes. You can have sort of the ASCII art control flow graph. I don't know how easy it is to navigate. Of course, the graphic user interface of IDA Pro is a lot more intuitive to use, but this is a free tool that works really well for disassembly, and so you can really follow the structure of simple binaries, at least when things get very, very complicated. You can always resort to saving the whole data structure or a subset to a dot file, and then see it in a graphic view. So you can actually do AG and then pass to the xdot command through a pipe, and it will show you a very fancy graphical look of or picture of the basic blocks in a program. So this is very useful. Also, we saw how ROP is really important in exploitation. Radar 2 has some tools to find ROP gadgets in the binary, and helps you to sort of like combine them together. Also, we have generic search, where you can find for a specific sequence of byte in the binary. You can set definitions. So for example, if you have a chunk of data and you want to be able to refer to this data as a data structure, you can, for example, say, hey, I want to define as a struct, something that has 16 bytes of length and has two integers, one called foo, one called bar. And suddenly it will, represent this data structure in memory, and you can use it in a way that is easy to remember. Okay, so little by little you can create these definitions, and suddenly your binary will be more useful. Another thing that is interesting are signatures, which are similar to the flirt signatures of IDA Pro, which is when you have a big binary that is being statically linked and stripped from the symbols, you might have tons of code that are just libraries. And so you want to be able to recognize these libraries so you don't waste hours of reversing binaries on the OpenSSL library, but you actually focus on the application only. This is super useful in IDA Pro. Sometimes saved hours and hours of analysis because you focus on the right stuff. And sincerely, I never use signatures, so I cannot comment more about it, but it is a feature that is interesting. And then there is R2 pipe, which is great because fundamentally you can write a program that sends commands programmatically to Radar. So you just import the R2 pipe package, and then you open, for example, our vServer program, and then you send a command, AAA, and this returns the result. So you can even print. So they will send the command print 4 instructions from where you are, and it will print it out. Of course, you can also parse the output And so, for example, here you would say, hey, I want you to override the binary at that point with a jump to this particular address, and these variables have been obtained by interacting with the program here. So this allows you, for example, if you have something that continually changes, you write a program so you don't have every time to manually do that, but you just run the program, reads the parameter, interacts, and modify the program the way you want. And we will see a demo in right now. So summary, Radar 2, very powerful, steep learning curve, personal, many people have personal opinion on debugger, disassembler, whatever. I suggest it as a tool. I find it very useful. It's free. Of course, if you have access to IDA Pro and you want to spend thousands of dollars in IDA Pro licenses, be my guest, but not in this class, especially because of the terrible F5, which takes all the fun of binary analysis away. Okay? So keep your cheat sheet handy. It's very difficult to remember all these different commands. And if you find something that should change, let the Radar 2 developers know. I mean, as Shellfish, I think we have at least one of the major developers of this tool involved. Two of the major developers too. And so they're always eager to improve the tool. I love their energy. I think they're doing a great service to the community. So please be nice. Just don't complain. Provide good context. And here I put a bunch of additional references that I used when I was completely lost in how to use Radar. They're pretty good. Here there are some more references that you could use to learn what to do. Another tool that you want to have in your sort of arsenal of tools is Metasploit. Metasploit is an exploitation framework. It was developed in 2003 by H.D. Moore, and then recently, a few years ago, it was acquired by Rapid7, but it's still free for non-commercial use. So there is a community edition that is, very nice. There is also a graphic user interface. I never use the interface, so I don't know how nice that is. And also comes with Metasploitable, which is actually a VM full of vulnerable stuff. So if you want to try, I want to try this particular exploit against this SQL server that is vulnerable, you run Metasploitable in a VM, and then you can play with Metasploit, launch attacks, see exactly how it works. I think it's incredibly useful, not only to get used to use Metasploit, but also to, if you want to generate attack code, you can put it on, do some SQL injection, see what is observed on the network. If you're developing network tools, there are a lot of possibilities right there. And it's free, and I would say updated quite often. Both Radar and Metasploit are available on Kali Linux. That is this security-oriented distribution of Linux. I found that Radar is better installed directly from Git. So the latest, absolutely latest, greatest, because it is in such continuous development that you want to have the latest version. The one in, for example, the Radar version on Kali Linux is a little outdated. So I complain with the Radar guys, and they say, hey, you're running something that is years old. Please move on. But it's useful. Kali Linux is useful because as all these tools are already installed, already configured, so it is very useful for that. We're going to take a small break, and I'm going to give you back your midterm. No, I'm not going to give you back your midterm. I'm going to give it to you Wednesday, and I'll explain. Yeah, sorry. I just realized that I have to. Yeah, it's a tease. Sorry. Tease. We're not going to do it now. Wednesday. I just realized that I forgot to rescore one of the questions. Okay, so we're going to go on and talk about, yes?
So you mentioned that debugging in Radar 2 is a little, you don't use it.
I don't use it. I'll show you why in a
So
second.
you mentioned there's an extension for GDB. That
Yes, I'm going to talk about it. So the general problem, when you're exploiting something, you find a vulnerability, okay? And this is what is supported by Metasploit. You choose a payload, something that you want to send on the other side. You choose an encoding, and you execute the exploit. Metasploit supports you as a framework through this. There are a bunch of different components. The console is the sort of interactive console. You can use also command line interface if you want to do scripting. You can use, just separately the component to generate payload, and then you can do, encoding or manipulation of shellcode. The module has a bunch. Metasploit comes with a bunch of module for, scanning, administrator, specific server types, and so you can really tailor your attack once you decide, for example, that a certain machine has, say, an FTP server. Maybe you use Nmap to actually fingerprint that particular server. Then you go to Metasploit, you go what exploits are available, you find one that matches the actual version that you found, and you can perform the attack. Yes?
Can we use this for binaries, or is this
Yes.
more focused on network?
It's for binaries. Yeah, Metasploit is fundamentally for binaries. So this is an example. When you start the console, what you get, after a bunch of time where he's setting up stuff, it has, I ran it a few days ago, so you can see there are 1,600 and more exploits. So these are vulnerability that are out there in the wild, that somebody developed an actual exploit for. That means that every time there is a new vulnerability, the new shell shock, you will see in all the mailing lists, oh, they already put it in, in Metasploit. Now, you just have to say, use this vulnerability. You press a button, you set the host, and you get a shell, okay? So this destroys the fun for a certain point, but also it's useful if you're, for example, pen testing, because one of the payload is the Meterpreter, which is cool because it puts fundamentally a piece of binary in the memory of the attack machine, doesn't drop anything on the file system, so it's very, if you want, hidden. And it doesn't just open a shell, provides you all sorts of commands. You can take, snapshot of the video, screenshots. You can, modify the user interface, interact with the user interface. Is an extremely sort of like flexible payload. So, for example, if you are in a capture the flag, dropping the Meterpreter provides you with access that you would not probably have with just a shell. You can do other things, but depends, on your needs. Summary: Metasploit provides a number of prepackaged exploits. To me, the real value of Metasploit is shellcode, it's payloads. Okay, the exploits, of course, they're useful when you pen test, you want to demonstrate, you find a known vulnerability, you can use one of the ones provided by Metasploit. But the cool thing is, like, when you're developing a new exploit, instead of painstakingly develop your shellcode, you go to Metasploit and say, okay, give me, the shellcode that does this. And most of the time, they have the shellcode, and you just use it. So it saves you time. Another tool that is useful is PwnDBG, is a GDB plugin, and provides fundamentally an improved GDB that gives you a better vision. So, for example, every time you step, you will see a screenshot with all the register, where you are in the current assembly, the current status of different parts of the memory, and that's really, really useful. Okay? So now we are going to look at our friend vServer. So this is an experimental class that I never run before. Let's see how it goes. So we have our server, and we have to break it. So this is similar to the process that you will use or that you have already used many times to break into one of the binaries. In this case, it's slightly different from what you're going to do, what you are doing for your homework 3, because we're going to do a remote exploitation. So we're going to attack a remote service. We have to run code in the remote service, and so we have the problem that just dropping a shell is not enough, because if you execute shell, you're not on that server, and so nothing happens really, okay? You need a way to control that shell. So one interesting thing, okay, let me, no, sorry. Let me just, I knew it. Sorry, guys. 1 second. Okay. Sorry. The server. Let's see. So, oh, perfect. You guys cannot see anything, of course. Now it's the time where this better, huh? So can you see this? Okay. So this is our code, the server. We don't have the source code in most cases. We have just the binary, which I have right there. And so the first thing, we don't know really what vserv does. So one way to do it is to use the strace command. Okay. And strace allow you to, the server takes -p, that the port that is listening on. strace follows the system calls that the program performs. So if I do strace the server, that's P1337, and this is going to be, you know, you can see that, of course, sorry guys, this is, okay, there's some interesting, yeah, sorry, I was attached to the program, so it doesn't have to kill me, so the port has been used. You want to, perfect, okay, so if I strace, you can see that there is a bunch of stuff, most of the stuff like what, but then you start saying, okay, there is a memory map, some memory allocation, then there is some open, read, close, it's looking for product, socket. Okay, great, it's creating a socket, that's good. Then set the socket option, classic reuse adder, so you can you don't have the problem of rebinding after the timeout. Then there is a bind, great, to port 1337, and there is a listen. Okay, and then do an accept. That's a classic server behavior, right? Create the socket, bind it, listen, and wait. So now, on a different thing, okay, sorry, we do nc localhost 1337, and we will see on the other thing, a wonderful thing happen. See, accept, clone, close, accept. So, oh, this is, you know, something that accept, create child, so forks. Clone is fundamentally fork. Close the existing socket and wait for the new socket again. So this is a perfectly normal forking server. Okay. So this is good. So use accept and fork and then reads. But we haven't seen the read because we've seen just the forking and thing. But we can follow the kid or the child by using -f. So let's try this. If we do this time -f, you can see that when we now connect like this, now you will see that there is the accept and there is the accept, and then we have a read. So you can see that fundamentally the tracing process has left the father and now it's starting to follow the child, and the child is waiting to read from the socket number 4 that was passed to the child. So this it's something that happens quite often, that there is a main server, you receive a connection, you fork, you pass the new socket to the child that decides what service is going on. Great. Since we are connected, here we can say ciao, okay? And we see we got ciao back, awesome. And if you look at this, you can see that there is read one by one of the letters, and obviously here there is new line and stop reading and wrote it back. Makes sense. So there is a read and there is a line. But now, apart from this, now we have a good idea just looking at the system call, okay, of what the program does. Is this always the case that you just look at the system call and you find out? No. Sometimes, if there is a lot of stuff that the program does in memory, for example, the encryption of a buffer or other things, you will not see any of that in the system calls. But oftentimes with network behavior, a good starting point is strace or strace or truss. Yes?
Does that integrate at all with GDB?
Yeah, with GDB, you see also the system calls, of course. This is a very, I would say, coarser view. GDB gives you a super detailed view of what's going on because you step by step every single, binary instruction, okay? And we will see that in a second. But so, first step, strace, and the thing. The important thing is now we have this forking thing, and it's annoying for a number of reasons because with GDB you connect to the fork, the port is connected, and then it's nice when you have these forking servers to create a version of the server that doesn't fork, that is just one program, okay? So to demonstrate a little bit the wonderful capacities or capabilities of Radare, we're going to turn this server into one that doesn't fork. So let's start with, you see, here we start Radare in write mode, all the analysis of the server. Don't worry if the numbers here, these are addressed, if they're not exactly the same as you will see on the screen, don't freak out. It's absolutely normal. So let's stop here. Let's stop here. Okay, here we're done. So here, R2-W-A VU server. Okay, so you can see I just start Radare here on the server and analyze, the various function, construct the control flow graph, and then drops us in the entry point of the program. This is, what in the ELF format is like start from here. That's not main. That's just the libc pre-main routine that will set it up. In this case, this binary has not been stripped completely. So if you look at here, you can do AFL and say, I want to see all the functions. Oh, that's a lot of functions. So this is everything that's been, you can do pipe more. Okay, there's ini, there are all these, symbolic things. We don't care, there is some implementation of write. But then we can see something that says manage TCP client. That sounds, at least promising, okay? So, well, let's start looking for main, which is also processing. So I do S main right here. And this will be, remember, S is go to. So set your location to main. And here we are. And analyze function information. This tells me a lot of stuff about main. For example, it takes 2 parameters, a bunch of locals. And you can see, for example, it tells me that is 983 bytes. So the main function is 983. And so, as you can see here, I can just print 983 characters as instructions. And this is my function main. And you can see here is the disassembly. You can see this is really where your push EBP, move EBP, and here allocate the stack for the function, initialize a bunch of variables. Let's go down. Here there is some string compare. This probably is checking something with the parameters. We don't care much about this. But you can see on the interesting thing here on the sides, you have lines that allow you to tell you where are certain jumps. So it helps sometimes to see exactly where you can have jump forward or backward. Is this the most legible form? No. It's not super useful at all times, but it's better than nothing. And you can go here. You can have for example, here you can see that whenever there is a string that is pushed on the stack, that push string.simpleTCP server is actually because there is in the binary a string called simpleTCP server, which it's part of a printf of some sort. And so you, instead of just seeing push a random address, it tells you, oh, that's a string, and the string is simpleTCP server. So this gives you more information, a bunch of printf. You go down, they're right, 0. There's a lot of function get proto by name. But let's not look at this. This is fundamentally the setup. Let's go down towards the end. Let's look for fork. Oh, this is very boring. So why don't we do something like this? We do the same thing, 893, oops, but we do grep fork. Oh, great. Instead of going through this, I just want to go where the fork is, and I know it's 08048C1C. Okay, let's go there. 08048C1C. Now you can see that this has changed to reflect that we are in a new location. And now, if you want to print, 5 instruction, you can see, oh, great. You see, these are the instructions at that location. You have a call to the fork, okay? Then you have the result of the fork that is put in this local variable. We could rename it to, PID. Then there is the PID is compared to 0. And if they're not the same, go somewhere else. That means another location. Otherwise, go to an error state. So if let's do 20 of this, you can see that here, the JNS 8048C57, it get here, okay? And here there is another comparison with 0. And if they're not equal, they will go and jump to this address. Let's go a little further. For example, let's do 30. Oops, that's way too many. Not enough. Yeah, here. And you can see that it checked if it's 0, and if it's not 0, okay, in that case, we'll push a word and we'll call manage TCP client. So you have to look at this and think in your mind, okay, this is the fork is receiving the PID. If the PID is not 0, they will just call here, push some parameter to this function, and you can trace what this is, but this is actually the socket that is returned from the accept. Okay, so it's fundamentally pushing the socket, the number 4, on the stack, and then it's called manage TCP client, and at that point, we know that the actual did happens. Yes?
So this is a ELF that we're analyzing.
Correct.
Not a binary?
It is a binary in ELF format. So ELF is the format of the binary. It tells how the binary should be parsed and loaded into memory. There are different formats for the same binary. Binary in Windows are in the PE format. In Linux and other architecture are in the ELF format.
But this code is like specific for an Intel chip.
Correct. This is x86 32-bit code.
How come
For
there's so few instructions, like, you know, range of instructions?
what do you mean? There are tons of instructions.
Like I thought Intel chips are supposed to have thousands of instructions.
Yeah, but that's a very good point. That's a very good point. And in fact, you see that you use mostly add, move, jump.
Yeah.
There are a ton of other instructions that are never used. And in fact, a way to know, for example, it's sort of a hackish way to know if you're decompiling crap, is because if you take random bytes and you try to decompile it, it will decompile, but it will have all these instructions that you've never seen before, like some, you know, support for the MMZ unit, and you're like, what? Most of the time, if you see add, move, jump, compare, jump, that means that you are actually executing the right code. Okay, so that's a good point. There are a ton of instruction, but they're not used as much. Okay, now you can see that we find the call to fork, so we can actually go. Let's refine the code to fork. So we're here. Now you can see that there is this call to fork. We want to change the binary. So for example, this instead of calling this, okay, does, for example, in these 5 bytes, we don't call fork. Instead, we simply set EAX to 0. That would be awesome, because that is, if I set here EAX to 0, instead of using these 5 bytes to call a function, I override these bytes in the file, and I will load 0 in EAX. So the side effect is the same. I can call fork, and fork will put EAX will put 0, because remember, in the child, 0 is returned. In the father, the fork function call returns the PID of the child, but in the child returns 0. So if I delete fork and I put a 0 in EAX, then the program will think, oh, I am the child, let's do manage TCP client. And you will have a program that does not fork, but does exactly everything like a forking program, which is very useful when you're debugging stuff. Okay, so this is the point. You can see here you go to the call to fork. And so this is another cool thing of right there. Here I can see print what would be the assembly representation of move EAX 0. Okay, so we can do it in, so if I go here, I do PA move EAX 0. And telling me, hey, if you want to execute move EAX 0, these are the 5 bytes that you have to execute. Okay, cool. So fundamentally, I have to take these 5 bytes and override it to these 5 bytes. Okay, that's awesome. Very, very simple. Okay, so we could do it. We're not going to do it because it would look awesome, and that was my first attempt at doing this. But then it wasn't working. Okay, actually, if let me do an example. I'm going to quit this. I'm going to take my friend the vServer. Oops. I call it vServer 2. Okay, and I want to make this the forking thing. So now I call R2 in write mode -A vServer 2. Great. I go to main. I do PD A93 pipe grep fork. Oh, that's the address. Okay, let's go there. 0x0804 8C 1C. I am right there at the forks. Let's print 5 instructions. See, here I print bytes, 893 bytes. Here I ask only for 5 lowercase d is instructions. Remembering this? What? How do you remember this? You do p, and it tells you all the possible variation that you have for printing. You can have, p, print as indented JSON, print Pascal Y0 terminated string. Everything is there. So, PD does it for me, but I'm sure there are quadrillions things that you can do with Radar and printing. This really shows you the power of something like this. In addition to the fact that you can, look at all sorts of different representation of the code, entropy. There is a lot of stuff that you can do. But let's not get carried out. Now I don't remember how you exit from kill. No, is that one? Q, thank you. See? You can also run commands like this. That's pretty good. So, but let's go back to our 5 oops. Because now we're not in our right place anymore. So let's go back to here. What? Okay. Okay. Sometimes you just have to do the right thing. Let's see. Much better. So you have your fork here, and now I can override this with my B8000. The super cool thing is that you can, if you look at this, you can just do write X and the file, and it will actually overwrite wherever you are with whatever you want. So you can even better, I could do write the assembly here of move EAX0. So this not only will disassemble this and find out what is the representation, will also write it and overwrite this. So this is my binary of vServer2. I do this, and guess what? Now when I do PD5, you see, now my instruction, instead of being fork, like here, now the instruction is move EAX0. So when I will execute this version of the binary, it will get here. It will put 0 in EAX. So now I am the kid. No fork has been executed. And I will jump to manage TCP client for the win, right? So great. Let's do this. And oops, quit. Now we do with server 2. And we run it. And so now when we connect with this, we do chow, we get it back, and this has terminated. Okay? Okay. Oh, yeah, sorry. So the problem here is that if I open bserver 2 in GDB, okay, and you can see that I go to pondbg now. Now this has been loaded in the binary. And when I run with -p137, this means run this binary passing these particular parameters. And actually, let's break disassemble main. And our fork is, wait. Wait. Now now I remember. Yeah, here we go. So here, where is our friend? The string error main signal. What was 08C string compare? That's not it. Sorry guys, that's where the unscripted part comes in. Let's see if I can find the move EAX0. C1C. C1C. Thank you. So here is the move EAX 0, and this should work fine. The problem is that this doesn't actually work as expected, because when you call to fork and there is a relocation, the 4 bytes after the EAX will be overwritten by the loader. And so you will end up moving into EAX a very large value, which will be EAX be positive. And so when compared to 0, it will not actually execute anything, and we'll just think that he's still in the father with a PID that is very high. And so you will have still a forking binary. So we have to do something more radical. Okay, so this is okay. So since the zeros after the B8 are overridden, because when the binary is loaded, the binary in the ELF, remember that at that location, it had to substitute the address of fork. So the fact that we put B8 and something, when the binary is loaded, it will say, oh, I know that these 4 bytes, I don't care what it is, I have to put the address of fork. And so even if we tell them to let 0, the moment it gets loaded, this gets overwritten. So instead of being move EAX 0, it's going to put move EAX some large values caused by the relocation. So this is not going to work. So we have to ignore this, okay? And instead, we have to fundamentally overwrite and making sure that instead of having a jump that is the result of the comparison, we just move here 0 in EAX, then we move EAX in this local variable, and we just jump to the location where there is managed TCP client. Okay? So think about it. We have to, in a way, modify this binary so that the net effect is there is 0 in EAX, and we jump to the address that we want. Okay? So first thing, we write the jump to the location that we want at this location. So we look at this. This is the location where there was the jump if the comparison fails. Okay? Here we substitute, sorry, let me go up so that, you see, here we have this JNS. We want this to be not just something that happens only if this is 0. We want this to happen all the time. So these 2 bytes, this instruction, has to be changed to a jump always to this value. Okay? So this is what we achieve doing, oops, sorry, that now, I knew it. Okay. So by doing this first, we write the assembly for jump absolutely to this at this location. That means that I say, hey, right there, go here and substitute these 2 values with the jump whatever you want. And you can see that we were lucky in this case because the binary code for direct jump is 2 bytes exactly as the instruction that we overwritten. Because one thing that is important when you're modifying binaries, I know they're going a little long, but give you a second. The cool thing when you modify binaries is that you have to keep track of the alignment of the instruction. You cannot just insert here a bunch of stuff because all the offsets will be affected by it. So you always have to override with what already is there. We were super lucky with this because our move EAX 0 was exactly 5 bytes like the one that we were overriding. So that was easy. But this is not the same. First of all, we want to move this instruction down here. So in order to do this, we have to write at this location this instruction, but we have an extra byte to cover. And so we use our best friend, NOP. So you see, so we write 8945E4, this, plus a 90, which is a no operation, at the address of this instruction. And after that, you can see that these two are identical, and then there is a solitary knob that won't hurt anybody. So now we have moved this. Now we can override this with the actual load EAX 0, right? So now, for example, to load 0 in EAX, we can do XOR EAX EAX, classic way to zero the EAX register. But once again, you can see that there is 2 bytes there, and we have to overwrite 3. So we're going to write 31 C0, which 0x, followed by a 90 at this address. So even our thing here tells you where we are in the binary. We can express operation and tell them to operate at a different address. So it's like create these 3 bytes and write them at this address. So now, you see, this will be ruined, doesn't work. Here we're going to 0 EAX, do nothing, put EAX in the local variable that represents the PID of the process, do nothing, and just jump to manage TCP client. Now we have a non-forking TCP client vServer. Yes?
What does the compiler use NOP for?
Alignment.
Okay.
Sometimes you will see NOP here and there if it has to align certain instructions.
I mean, wouldn't it want to avoid using that to make it harder?
If they can, yes, but
Also, optimization of pipelines.
also?
Optimization of pipelines. Optimization on pipelines.
Oh, optimization on pipelines. The expert. Absolutely. So now we have the no fork. Of course, you see that this is a very manual process. What if you recompile, you add an instruction to your source code, you recompile the server, and now you have to do everything again? That would be incredibly painful, right? And that's why we have our 2-pipe. And I found this to be really awesome. I know, awesome in a super nerdy way awesome, but still awesome. So look at this. So this is a piece of hacking code that you can see that here set some stuff, and here it's a Python script. Here go at mains and look for the fork call, okay? And then you can see that if I want to find out what is the address of the fork call, I just take the result, I split it, so it's just a string, and I know the call address. And the next command is like, go there, call adder. And now all the commands that I done by hand, I can actually script. I go in that location, and then here I print the instruction there, and you can see that, here you can start with, first you remove the first fork with the 5 instruction, and then you fundamentally extract the information from the code. This PD4 prints 4 instructions. The jump line takes all the lines returned by that, parses them, and find out the line address, the line target, and then create, remember the jump? I can now write it in a way that is symbolic. And so even if everything changes, I will just run this program and will just remove the forking part from the program without me having to do by hand every time everything. And you can see here is the same thing. I can find the instruction that I have to replace. I add 90. And of course, this is very hackish. It's just a serial commands in a script. But the fact that you can actually send commands, obtain the results, and save everything in a file allows you to repeat it as many times as you want. And I found that to be extremely useful. We're going to take a 10 minutes break. So now we have removed our fork, okay? And now we want to overflow. So let's see. So the cool thing is, like, once you have a non-forking server, you can, you know that we're going to go to manage TCP client, and we can start to analyze it. So this actually, it's one of, come on.
Excuse me, can you put the mic back on?
Oh, yeah.
the assembler. Beyond this assembler is the printer. Take one, give it to other people. So this is our function here. Alejandra, at the end of the quarter, you're going to be like, sorry. All right. So now,
Perfect. Now it's green. Okay. Oh, and now I'm confusing this guy quite a bit. So we have our non-forking, and it's awesome because every time we execute the program, it's just one run. There is no children being forked. And you will see that the numbers on your binary are slightly different, but the concept is more or less the same. The interesting thing, at the very beginning, one thing that you usually look for is the stack adjustment. Here is, you probably have 408 in your binary thing, but fundamentally here is adjusting for the local variables. And so this is something that immediately tells you, okay, this function has something relatively big because this 400 is 1024, so maybe there is a buffer or a big data structure, etc., etc. But also, if you look then, there is this compare to the character 0xa, and if they're equal, they go to 5f, which is here, and then, of course, this is a no-op goes here. If it's not equal, it goes to 21, which is up there. So there is, you recognize that there is a loop in some way that is terminated when a new line is read. Okay? So the basic idea is you look at the code and you understand that there is a loop and that there is a condition that does not depend on the size of the buffer. So this is a good indication that there is some kind of buffer overflow. You put in stuff in thing, but you only stop with a new line. So here you already know that you have a buffer, there is 1024 characters, so you can start sort of like think about it. So the first thing that you would do in a situation like this, for example, you can break manage TCP client. That means that, as you know in debugger, whenever you get to that function, you want to stop. That's a typo. It should be just, you can shorten for B. And you can say, oh, and stop and manage TCP clients plus 86. If you look, I don't know if 86 is exactly where you are, but the problem is 86 is right after it exits from the loop. And this is very useful. So here you would go, I can see break, manage TCP client, and I remember here, let's say right before the write, I could stop, I don't know, write, where is our EA comparison? Here it is. This is plus 99. I want to stop here, you see? Because if this is the loop, and you can see that there is some looping thing, okay, because here I am at plus 96 into this function, and it's going back to plus 33 that is up there. When I get here, means that I just went to 6C, here, 6C, and so this is a good point to stop because I'll be out of the loop and I can see if what I sent has caused damage or not. Okay, so let's see. I can see manage. What did I say? 99. Okay, and so you see, it created a breakpoint exactly there. Creating these breakpoints in important points in the program is important because that's how you determine what's going on. Now, the interesting thing also is if, for example, no, yeah, I have to run, sorry. I run the program, start the server. Now, we know that the server is listening to a connection. Before we get to manage TCP client, of course, we have to call the server. And at this point here, you see, we just breakpoint in manage TCP client. This is a cool thing, for example, that GDB doesn't give you, but PwnDBG gives you. For example, you have your start trace. You can see that there is, libc calls main, and main calls manage TCP client, so you know which function has been called in that particular path. The stack and how the stack has been modified. The disassembler where you are, so you have a good idea of what's going on. And the cool thing here is, you can execute stuff, and everything is sort of like change accordingly. Now I'm gonna have to use the right key. I knew that. No. Yes. Here you can see also the registers. You see where they are. So you can see at every step everything that is there. And if it can tell you something additional of how the register were modified, it will tell you. So it's very useful to have this, this kind of extended debugger that is better than than a normal GDB. Somebody was making me notice there are other debugger helpers, like PETA is a one that many people use because it has also additional information. It's up to you. As a debugger, you can choose whatever you want. It just cannot use a decompiler. That's the only level of importance. So in this particular case, we just enter the function. So one thing that is always useful is this. Let's see. 1 second. What do you think this is? Good job. So there are two values printed. I'm asking you to print two 32-bit values as integers, okay, at EBP. But what does the address of EBP contains? What? Speak. So the EBP pointer. So EBP is FFFFCF68, and at this address, so on the stack, there is the saved EBP pointer. And after that, what's that? The return address. So this is something that say immediately, okay, we are going to overwrite this value. If we can get this value to point to something that we want, then buffer overflow succeeded. So this is always a good check to print, the two values after EBP, because it tells you the saved EBP if you're doing some EBP override, or the return address. Okay? I know that for some of you this is super basic, but for others is not. So you can see here in the slide. Also here, for example, you see what the stack is, the current thing in the stack. And so you can run it and try to send a long string. For example, you can do Python, this value, pass it to localhost, and see what happens. So let's rerun in our debugger. Now that we understood all this stuff, we rerun it. And this is great. Note, this works because we don't have a forking server. Because I always say, do you guys watch The Good Place? The series The Good Place? So it's about a woman who goes to the good place, so paradise. And in paradise, you cannot curse. And this woman is a horrible woman and curses all the time. But every time she tries to say the F word, it becomes fork. So every time I say, this is forking, it's like, God, okay. All right. There's a lot of shirt and fork. So the good thing here, because one thing that I haven't told you, that this removing the forking aspect of it, removing the forking aspect of it is actually not necessary for debugging, because with GDB you can set follow child to true. And so, like, remember strace, we run with F and follow the child. In debugging, with a GDB, you can do the same thing. You can say, whenever something forks, stop debugging the father and go, or the parent, and debug the child instead. The problem is that when you have to rerun, then the father is still listening to the port. So it's going to tell you that the port is already in use. It's just painful. Thanks to the fact that we have removed the fork, now we can rerun anytime we want. Now, I want to set a very long string. So I guess it's going to be Python print A. Let's do A. Let's do B. Let's go crazy. Like this. Pipe nc localhost 1337. Okay, so this is now running. The moment I do this, I am in manage TCP client, but I haven't read yet. If I do now continue, it will go to the NOP after the cycle. So if I do continue, it will read everything that I've sent and then stop right after the loop is over. So I do this. Great. And now, if I do the same EBP, you can see that our saved EBP and return address have been obliterated by 42, 42, 42, which is the ASCII code for uppercase B. So this is great. Having the return address to some crap is the most important thing. Here you can say you control EIP. Now you can jump to whatever instruction you want. Now it's time to build your actual exploit. So now I know that I can influence that, but it's not really enough. Okay? So the next thing, you have the payload. Now, this is where your Metasploit thing comes in, because yes, you can just have bin shell, but if you do bin shell, it's going to write, execute bin shell, but you will not see anything coming back to you. You will not see input and output. You can execute commands, but you want to do a lot more. Yes?
How do you know how much garbage you need to pass in before you can pass in the register?
So, very good point. Do you remember at the very beginning we saw that the stack was adjusted by 408? If you look at the first three instructions in your debugging, the third one should be sub ESP 408. And this is because actually when the program starts, apparently there is something that is saved EIP, then saved ABP, and then it creates a buffer that's 1024 plus 2 integers. One is actually, if you read and try to understand, and I suggest as an exercise, try to understand what it does, but I can tell you that one of these is a pointer into the structure, and that's how the read goes. And the other is an integer, which is actually a copy of the socket that was passed to TCP client. Okay? So you see that something has been subtracted for 1024 plus 8 characters. So I went for 1040, and I saw that I overridden. I can say maybe I'm going to start 1024, and then I see that I don't override. Eventually, you get to the point where you override. You go by attempts, right?
So we're basically just guessing. No.
You're not guessing, because you know that actually, since here you have no stack randomization or anything, you can be incredibly precise. You know it's exactly 1024 character will do this, and then 4 will override this, and 4 will override this.
Okay.
Bottom. ESP, the register ESP points to the,
So for the buffer, so buffer is 0, buffer index 0, would that be at the very, very bottom? Of your
right here. This is 0. And then it goes up like this.
Okay. I mean, sounds different.
Are you entering the Lucas school of thought?
No, it gets confusing.
Yes. Okay. So imagine that the stack goes from left to right. Okay. So your stack is like this. Okay. And the stack grows in that direction. Okay. But this is 0, 0, 0, FFF. Okay. So this is your saved EIP, saved EBP. This is where it's your buff is allocated. This is your pointer. This is your file descriptor. And you write like this. Better? Yeah. It's, sincerely, this is a matter of perspective, mental image of memory, and upbringing. If I have to think about, because going up or down, between me and Lucas, I think that we have many pros and cons that we can discuss ad nauseam, but I understand that having a horizontal stack is probably the most intuitive, because then you can see the strings exactly from left to right. Up or down, down or up, all bets are off. Yes?
So once you've figured out how to overwrite the registers, how do you decide what
You don't override the register. No, you override the stack.
stack?
But that information on the stack is going to be used when you return from a function. Okay? So when managed TCP client was called, the return address was saved here. Okay? And then somebody saved the EBP. We don't care at this point. But we have a loop that reads from the network and writes in memory that will stop only when we give this character, not when the space is over. So we can override this thing. When managed TCP client has to return, we'll take this address and jump to it.
But how do you decide what to overwrite that with?
I'll tell you right away. So first of all, we have to decide what happens. And this is, we will get to that. So we open Metasploit, and we can say, hey, I want to use this Linux x86 shell reverse TCP. That means I want some shell code that when it's executed, calls me back. Okay? So I will have, this is the server that I'm attacking. Okay? Right now we're doing everything in one computer, so it could be a little confusing. But in a real situation, here's the server running with server. Okay? And here's the attacker. So when you launch a buffer overflow, the code that you executed is executed on this computer. So it will do things, but what if you want to find a file? You want some interactive access. Okay? Well, one way to do it, there are many, is to write some code that actually connects back to you, let's say to port 444444, and drops you in a shell. Okay? So this guy, this code, shell code, will open a connection to a host that you specify at a specified port, and the moment there is a connection, will drop you in a shell. Okay? And this is, and you can also have shell code that binds a port here, and when you connect, you drop in the shell. They're very, variables, and depending on, there could be a firewall, for example, here that doesn't allow anything incoming, but only outgoing. Then you need a reverse shell. Okay, you have to think about what you want to do. So you can see here that I said, I want you to connect to host 127.0.0.1. In this case, would be the IP address of my client. Since I'm doing everything on the same machine, I'm using localhost, and connect to the port 4444. And then I just do generate, okay? And this is like generate so that it looks like a C string. This is the type of code. And here it is, a fantastic unsigned char buff with my shell code. Ta-da! Pretty easy, right? So now that you have this, you just, of course, put it in your, oops, you put it in your, little check for shellcode. So you call it, you remember, like you did with the other buffer overflow, okay? And then you just build the exploit. Once you verify that it exists, for example, in this case, I think I even have it. Come on. So here, if you look at, that's the shellcode. So actually a bunch of, this is a local shell bind port. I will planning with, but this reverse local 444 means that if I run this program, since this jumps to this shellcode here using a function pointer, what happens when I run this? I will set up something here that does this nc listen to port 444. Okay. Then I run my test shellcode. And now this shellcode has connected here. So here, oh yeah, look, I have a shell. Fantastic. Did you see? I was listening on port 4444. When I run the code, the shellcode, I got a shell here. Okay? Did you understand what happened here? Who didn't understand what happened here? You didn't. Perfect. Okay, it's important. Because first of all, never start an exploit unless you're absolutely sure that your shellcode works. There is nothing more frustrating than wasting a ton of time and then say, are you sure your shellcode works? And then you find out for some weird reason your shellcode was not doing what it's supposed to be doing. Here, we're just testing the shellcode. We take this thing. So we have this test shellcode here. It's just, this is not the attack. This is just, a way to take this binary code and using this technique, which is just setting a function pointer to point to this code. Go for it. No problem. It happens. So I'm just fundamentally have a C program that jumps to this and executes it so that I can actually check what happened. This code here is code that I generated with Metasploit. And what it does, opens a connection, a socket, to port 444, and then sets up the input-output and drops in a shell so that you get a connection, and then you can do ls, you can do any command you want.
So it's just like the shellcode you provided in the slides in the application security suite?
Yes, that's the first one. This one, see with bin shell at the end? This is the shell code that just opens a shell. It's the most basic shell code. In this case, if I use in this attack that shell code, it wouldn't work because it will just execute bin shell and just wait for command from standard input, but the socket that we're using is socket number 4 that is passed as a parameter. And so it will be a shell, say, yeah, you have a shell, but you cannot talk to it. So apart that it's super cool to have a shell, you cannot do anything. So you need something that calls you back, opens a shell, and sets the input and output so that they're actually associated with the socket and not with the terminal. And so then you can, do ls. Actually, if you take this and you load in a disassembler, you will see all the steps. They do open socket, they do dupe, so they duplicate the connection, and so they fundamentally redirect their input, output, and error to the socket file descriptor. Clear now or not clear yet? Ask question, yeah.
The result came out that you have remote access to the shell.
You have remote access to the shell, yes. Thanks to this. So imagine the situation without this, okay? Without this, you would call into, you would execute some call, and here you would do exec v bin shell, okay? So this v server the child, will become bin shell and would wait for commands from the standard input, which is descriptor 0, and will print the output on the standard output, which is descriptor 1. Unfortunately, this socket happens to be 4, so that it's not going to work. Okay? So we need something that executes something that opens a socket to this, and then use this socket and launches bin shell by redirecting input and output to this socket. So everything you send is interpreted as a command to bin shell, and everything that is printed by bin shell will come back to you. Okay? All right. Yeah.
Could you do a bin shell listen on 4?
No, because if you just execute bin shell without doing the redirection first, well, you could have some shell code that would actually close the input and output and redirect to the socket and then drop to the bin shell. That would be, an interactive one. That's another possibility. But, there are all these payloads that are ready for you by the thing. So now that you want to do the exploit, we know that the buffer is 1024, at least that's our thing. We remember when we were looking at the stuff before, oops, sorry. Oh, sorry. Oops. Okay, exit show. Thank you. Die. Better. So here, there is an interesting part, which is I want to print what is ESP. Okay, so FFFFCB74. That's the beginning of the stack here. Okay, in my program. So I know that my shellcode will start something like here. So I'm going to put here my NOP/SLAD, and I will have this jump somewhere here. Okay, so now I'm going to do exactly what I do in the basic exploitation in what I do locally. So I take the length of the shellcode, minus the byte size, divided by 2. So I put it in the middle. It's not necessary. But I first start with NOPs for the first part. Then I put the shellcode. Then these 2 NOPs have been added for alignment. But fundamentally, after that, I have the address, which is this FFFFBC. Remember, it was 74. I went, 16 characters later, 84, just to jump somewhere in my buffer. And then I print the buffer. So the basic idea, this will overflow the thing. And let's see if I haven't changed anything. It should actually exploit the whole thing. So here on one window, I have my vServer. Oops. Wait, I have to kill this guy. Here I have my vServer. This is a forking server, absolutely normal. And here I have my NC444. And now, if I have, if I do exploit, Python exploit, it will print a bunch of stuff. You can see that there is the bunch of NOPs, of course, unprintable, some weird shell code, of course, all unprintable, and then a 4-byte address repeated many times that eventually will overwrite this value with a value in the NOP/SLAD. And it will execute the code. So if everything works, I pipe this to NC localhost 1337, localhost 1337, and here I have a shell. Okay, so this is something at this point, you find your secret, you find whatever you want, but the basic idea, again, find the vulnerability, control the return address or whatever pointer, function pointer, get your shellcode, for example, using Metasploit, and then put together the exploit, launch it. Remote or local, the difference is not that big. The thing that is difficult remotely is when you don't know anything about the platform. So you send fundamentally an input and you see a segmentation, so something crashes, but you don't know where the stack is, you don't know what platform is. That requires a lot of trial and tribulations, and sometimes you just can't get it right, and it's very difficult. Yes?
So how would your analysis change if you knew that the remote code was maybe open source and that it was 90% unmodified or something?
That's very good. So if I know that it's if I know that it's open source, I can recompile it. And yeah, if it's been tweaked slightly, depends. I mean, if it's been tweaked slightly in some position has been moved, I can try to use, for example, an attack that would leak some addresses from the stack that gives me an idea where the stack is or where the code is, if I can get to a function pointer, and I can reconstruct what it is. Oftentimes, especially if it's not been tweaked and it's just a package that's been installed on a system and there is no address layout randomization and so forth, you can predict quite well where the code is. The thing that is good, and that's in these cases where you have uncertainty, having large buffers and being able to use large NOP sleds is really important, because then you can be more or less blind. You know, do you overflow with something that is in the vicinities? And if you have 30 megabyte buffer, the chances of getting in the right spot and executing the shellcode are pretty high. Sometimes you have to brute force and do multiple attempts, but your chances are pretty good. Yes?
When you were mentioning the alignment thing, is that basically just for like a 32-bit binary? You have to start with the ones that it's multiple for?
Yeah. So fundamentally, it's a when you're in GDB, it's a trial. You launch the strings, and then you see, and you notice that the override for some reason was not calculated right. I might have, totally screwed up something in the calculation, but I observed that, of this 4 byte, only 2 were overridden. So obviously there was some, and they were in the wrong order. So I just added 2 NOPs, I move everything a little bit, and then the override was perfect. NOPs are great for, alignment and making sure that the size of your code is the right size. Yes?
Does this again only work because you knew the location of the code?
Correct. I mean, this works because I could run the binary in my local version, GDB, observe where the stack is, so I know exactly the location of the stack. There is no layout randomization, so the stack is always in the same place, and so on and so forth. If I had to do the same thing to something that is completely unknown to me, so I just send a string and I see a segfault, there are a lot of unknowns. I could not even know the architecture that I am, attacking. So there is quite a bit more that goes into when you are completely blind and you try exploitation. Other questions? No?